Okay, welcome everyone. So let's wait for 5 more minutes to see other people join. Okay, so we'll start sharply at 3:05. Okay, so I guess no one has joined, but we'll start as per our schedule. So welcome everyone. This is NOC 139 NPTEL tutorial on microelectronics devices to circuits. The course instructor is Professor Sudev Das Gupta from IIT Roorkee. I am Debashish Nandi. I am a PMRF scholar from IIT Kanpur. So as you know that we go live every week from 3 to 5. These are some of the prerequisites we had several times reiterated. So you must be aware of this. So today is 6th October and we are at week 11. There will be one more week and followed by one summary session. Okay. So I will have that announcement at the end of the session. So as you can see that I am in a different setup today. So I will keep my video off for this session. Okay, because there are some background disturbances. So let's move on. Yeah. So as we have been discussing, the first problem we are asked to find out the pole frequency, that is the high cutoff frequency for the common source amplifier shown in the shown in the figure given below. Consider that these are given. Okay. So what do we know about common source amplifier? A general Bode magnitude plot. Bode magnitude plot will be something like this. So this is your voltage gain, let's say. This is in your dB scale and this is your omega, right, in log scale. So it will be something like this. So what is this frequency? This is corresponding to the lower cutoff or omega L or the lower pole P1. We have discussed this multiple times and this is the omega H. So we have been asked to find out what is this frequency. Okay. So now as several times we have pointed out that this pole is corresponding to the coupling capacitances and this pole corresponds to the input capacitance of the input equivalent capacitance. Okay, fine. So now what do we need to find out? We need to find out this. So first we need to find out, we need to find out what is my C input equivalent. Okay, so how these capacitances are there? So this is your CGD, this is your CGS, and from this to body there will be a, let's say this is your body node, so this will be your CDB, and you know that body and source are grounded, so this you can directly short. Okay, so now what is required? So this, what is your input and one input side, by the way, this is your input, right, and this is your output. So you have one capacitance which is connected between input and output. So how do we resolve this thing? This, let me add another page. So basically, we resolve this. CGD will be resolved to input component using Miller's theorem, right? What is Miller's theorem? We know that if this is a system, let's say the forward path gain is gain is A, and we have a impedance connected between input and output. Let's say this is input, this is output is Z. So we can resolve this Z into two components, right? So how can we write this? This can be written as, this is your A, the gain of that path, and this will be your Z1, and this will be your Z2. Okay, so this is your input, this is your output. So what is your Z1? Z1 is basically 1 by 1 minus A times Z, and Z2 is 1 by 1 minus 1 over A times Z. So this we have discussed multiple times and also have pointed out where you can see the proof of this theorem from. This is very easy. You just need to compute the input and output currents and equate them, okay, through the coupling branch or the feedback branch. So now let's say in our case, Z is equal to what? 1 over SCGD, right? So Z1 will be what? Let's say 1 over SC1 will be equal to 1 minus 1. What is the gain of this amplifier, by the way? From directly looking at it, gain, you can directly write that it is GM1. It is GM1 given times RL. Okay. If we ignore the output capacitance bit or the R naught, small R naught. So this is what? This is your GM1 times RL. So this is your GM1 times RL minus of that times your 1 over SCGD. Fine. So your C1 is becoming as CGD times 1 plus GM1 RL. Similarly, your C2 will be CGD times 1 plus 1 over GM1 times RL. Okay. So now if you see your common source amplifier, so this is your RL, and in this place you have your R in, this is your C1, and this is your CGS. So your total C input equivalent is C1 plus CGS, that is 1 plus GM1 RL times CGD plus CGS. So your GM1 is given as 4 millisiemens, RL is 2 kilo ohms. So your this figure is minus 8. Okay, and CGD is 10 femtofarad. So this is 1 plus 8 times 10 plus your CGS is given as 33 femtofarad. So it will be your 123 femtofarad. Okay. So what is your R in? R in is given as 10 kilo ohm. Okay. So what will be your F of H? F of H is what? F of H will be your omega H over 2 pi. Omega H will be what? Omega H will be your 2 pi times tau h, that is your R in times C in equivalent. So this will be 1 over 2 times pi times R in is your 10 times 10 raised to 3 times C in is 123 10 raised to minus 15 hertz. Okay. So if you solve it, you will get the value to be 129.39 megahertz. So your FH turns out to be 129.39 megahertz. Okay. So I think we have done now a couple of problems regarding this kind, how you can find out your omega H and omega L. Okay. Suppose in this question, if I ask you that what is your omega L, what would be your answer? So omega L is basically depending on your the coupling capacitances, right? The capacitances you put your input and output via via the coupling capacitances. So as it is not given, so as I have mentioned it earlier also, so this curve will start from here. Okay. So at your DC, your omega L will be almost 0 hertz. So it will be kind of a low pass response and not a band pass response as shown. So remember that point. If such circuits are given and you are asked to find out omega L or FL, you should directly write that it is your what do you say? It is your 0 hertz because there is no coupling capacitances. And if higher order capacitances are considered, then you can see that there will be another pole and there will be another drop. Okay, that also we have discussed 3 sessions back. Fine. So now moving on, I think this is pretty straightforward. So please try this one. What is the trans resistance amplifier? Okay, so trans resistance, another trans resistance amplifier. Okay, amplifier. Another one, let's say trans conductance amplifier. Another two will be your voltage gain amplifier, and there one will be current gain amplifier. Okay, so input and output. So input and output you need to mention in terms of currents and voltages. Okay, so what is the basic definition is that basically what kind of matrices you use. Okay, so if it is input and output is related by your impedance matrix, so we call it as a trans resistance or trans impedance amplifier. If they are related with your Y matrix, then we call it as a trans conductance amplifier. And these two you can your in case one you will use ABCD matrix, in another case you will use your hybrid matrix. Okay, so this is the definition basically. So if your trans resistance means this side it will be voltage, this side it will be current. Okay, and trans conductance is this side voltage, this side current. Voltage Here also voltage, this side also voltage. In this case, current this side, current this side. So in our case, current is input, voltage is output. Okay. By the way, this one is this one. So now, can you give example of the second case? So can you give example of a transconductance amplifier we have been studying? You can unmute and tell me example of a transconductance amplifier. Yeah, anyone? So I am not sure if you are speaking Partsarthi because you are not audible. So I think you guys know the answer anyway. The transconductance amplifier, basically we have seen MOSFETs, right? Because what is the input? Input is your VG, let's say. And what is the output? This is what is the output, right? GM times VG minus VS. In this case, 0. So GM times VG. So output is current. Input is voltage. And the key defining parameter GM is your transconductance. Okay. This is your ID that is flowing. So can you see immediately that your GM is basically related to some sort of Y parameter, right? From this definition, your GM or transconductance should represent one of the Y parameters. So what parameter should it identify? If this is your port 1, this is your port 2, basically your Y21 corresponds to your GM. Okay. So remember that last time I have given you the vector network analyzer example, that how we measure the frequency. So similarly, if you have your VNA, let's say this is your port 2 and port 1, and you connect your DUT. DUT means your device under test. So if you connect your port 1 at this side, gate side and drain side is this, and this is, let's say, the MOSFET. Fine. So what you will see, how we generally measure GM. Okay, I am just going into that part. So you first measure S parameters, convert to Y parameters. You take GM as the GM is directly related to real part of your Y21 parameter. Okay, so this is how you measure your GM, and that will be a frequency dependent quantity. Okay, so what we have been discussing in this course is the zero frequency transconductance or the DC transconductance. Fine, but that GM actually changes with frequency. If you consider your Y21 small signal high frequency parameters. Okay. So in this way, you can define multiple combinations. For example, your current gain amplifier, one example you could think of as BJT. Though it is not absolutely necessary that BJT has to be a current control current source, or in that case current gain amplifier, but that can be represented. Okay, your IC by IB. Okay, so your beta then is related to these two impedance matter, these two port network parameters. Okay, so I think that is what I have to say from this one. Again, for an amplifier or any other system for that matter to be stable, the pole should lie in the dash of the S plane.
Left half. Option A.
Why? Why? So this is your S plane, right? So basically, what is happening is, let's say this is you are having a transfer function. Okay, let's say 1 over S plus A, and let's say A greater than 0, and H1 is this, and H2 of S is 1 over S minus A. So what is the pole location? So P1 is your at
A.
minus A location, at
And
P2
B.
is your A location,
Left.
right? So let's
Yes.
say this is your P2 and this is your P1. So you know, right, that poles are represented at cross and zeros are represented as circles, right? Fine.
Yes, sir. Fine.
So what is the time domain response? And how do you take time domain response? You take the inverse Laplace,
Laplace.
right?
Inverse Laplace.
So it will be simply e
E to
raised
the
to
power
minus
AC.
at, and in this case it will be at. Is that okay?
Yes, sir.
So in one case it is decaying, in one case it is expanding. Okay.
Yes, sir.
So what system do you think stable?
And decaying.
Why do you say that?
Uh, when the transient will die out, then we will get the desired result.
Because in one case you will never get a steady state, right?
Yes, sir.
In one case you will get a steady state. By the way, can you tell me in this regard, if let's say what is the let's say we are discussing only about P1, okay? So this is
Okay.
unstable and this part is stable. So can you tell me about what is the value of, if I, for this particular pole for P1, at what value of time the decay will be 2% of the final value, or 5% of the final value. So 2% is related to your 5 tau, right? And
Yes.
5% is related to 4 tau. So what is tau in this case?
Uh, 1 by A.
Tau is 1 over A, right?
Yes, sir.
So if from this question, if anyone asks you that what is the 2% settling time or what is the 5% settling time, so you can easily answer, right, for a first order system.
Yes, sir.
Okay. So by the way, uh, is it necessary that for a system the number of poles and number of zeros has to be same? By where is the zero on in this case?
Sir, I don't know the physical relevance of this, but when we plot root locus, then
Yeah,
zero originate from the pole and end terminate to zero, so that should be equal on paper,
exactly,
but
exactly.
physically what it mean
No,
I doesn't.
that is right. If when you draw your root locus plots, you see that your roots of the, or let in other sense, the loci will originate at pole and finish at zero. So in this case, where is the zero?
Infinity.
Exactly, right. So in this case, your zero is at infinity. So your root locus will be something like this, right?
Yes, sir.
So you guys know about these concepts, right?
Yes, sir.
Okay, good. So then let's move on to the next one. An inverting amplifier has RF is equal to this and R1 is equal to this. Determine the amplifier circuit voltage gain. So this you must have studied in the first year or the second year of your basic electronics class. So what is the gain? By the way, before going to that, uh, tell me something about this thing. What do you mean by ideal op-amp?
So there is many property of ideal of them.
Yeah, yeah, just spell out. What is the first thing?
CMMR should be infinite, gain should be infinity,
What?
uh,
Which gain?
which gain,
Open loop gain, right?
yes,
Open loop gain should be infinity. CMRR, let us not go into that because that is not relevant in this case. Yes, obviously it can be made relevant, but the discussion will be a little more complex. So one thing is that. Another thing, what about the input impedances?
uh, very high,
So in case of ideal, what is very high?
infinite,
For one port or both the ports? For both the ports, right? Because two of the ports should be identically looking same.
yes, तो कोई भी पोर्ट होगा इनपुट तो मॉसफेट से लाएगा तो वो तो इनफाइनाइट ही होगा.
Not necessarily. What if there is a feedback with drained input and output? Suppose if I give you some kind of circuit like this is your input, but there is a feedback connected. So will the input impedance will be infinity? It
No,
will
sir.
not be, right? So it doesn't
Yes.
matter that if it is in the gate or not. There may be another parallel branch. You do never know. So do not be misinformed about this thing. Okay.
Okay.
So what is the key point in analyzing? Okay, just let us start analysis of this. So what is the first thing I should consider here to find out the V out by V in? One thing is that this there is no current flowing through these two branches, right?
Yes, sir.
Another thing is that I need to know somehow the value of Vx. So V
Yes.
in minus Vx over R1 is equal to Vx minus V out over Rf. So your V in over R1 is equal to Vx 1 over R1 plus 1 over Rf, and then V out by Rf. So can you tell me how should we proceed from here? I need to find out Vx, right? So can you comment on this? How should I find out Vx? There is something called virtual short. Have you heard of that?
Yes, sir.
What is that?
We V1, V2 are at same potential. Potential difference is very small, so we can say that it is virtual short.
So V plus and V minus are same, right?
Yes, sir.
So this is coming from the fact that your CMRR is what? Differential mode gain divided by common mode gain. If your common mode gain is 0, then your CMRR becomes infinity.
Yes, sir.
So common mode gain 0 means under ideal considerations, you can assume the virtual short condition given there is additional condition that OPAMP should be connected in a negative feedback. Were you aware of this point?
Connected in negative feedback only.
Are you aware of this point that to assume the virtual short condition, you need to have two important condition. So basically, virtual short has two conditions required for that. One is open loop gain infinity. Another one is OPAMP should be connected in negative feedback. So without this two condition, if any one of them is not valid, so you cannot make the virtual short approximation. Okay.
सर पॉजिटिव फीडबैक में क्या दिक्कत होता है?
Positive, in case of positive feedback, you will not have that virtual short condition. Your V1, V plus and V minus will not be same. The
Why?
point why it will not be same.
Yes, sir.
For example, if you are pushing some input, okay, that input will. So let me just explain the negative part first. So you will
Yes,
by the corollary I can give the analogy. So let's
yes,
say if V in is increasing, right? So if
Yes, sir.
V in is increasing, so V out will be what? Decreasing.
Yes, sir. Decreasing.
So this is your negative feedback scenario. Now suppose you are pushing your signal at this point, okay? And
Yes, sir.
somehow by increasing this value, you are increasing your V out, and that same V out you are pushing it into again this positive terminal. So your negative terminal remains same while your positive terminal is keeping increasing. So your the difference between V minus and V plus will keep increasing, right? Until unless it hit the oscillation limit. So then it will start to oscillate. Basically what is happening, okay, let me just show. So let's say, okay, just maybe I have not explained this correctly or more clearly. So this voltage you are increasing, right? So what is happening? This voltage is increasing. Okay. So
Yes, sir.
now the difference of these two voltage will get amplified. So
Yes,
the
sir.
difference is decreasing. That means this voltage is decreasing.
Yes, sir.
Now if this voltage is decreasing and this voltage is increasing, so more current will flow from this place to this place.
Yes, sir.
So this will pull down the voltage at this point. So you see that at this node there is a opposite scenario, means it is not allowing this Vx or V minus to go beyond a certain value. Okay.
Yes, sir.
And that certain value is getting, so this is your summer, this is your gain block, this is the beta, this is positive, this is negative. Okay. So basically what you are doing, this is your actual path, and by putting this feedback you are basically subtracting with the desired, and you are checking what is the error of the signal. Where are you checking the error of the signal? You are checking the error of the signal at this point. Okay. So
Yes, sir.
if your error is more, then what you will do, you will pull down this, so automatically this error will drop.
Yes, sir.
Are you able to visualize that?
Yes, sir.
So in case of positive feedback, what is happening, let's say you are giving your input,
Sir,
let's
I
say
understood. Sir,
you
समझ गया.
understood, right?
Yes, sir.
So basically to have a virtual short means you are fixing the V plus or minus to the others voltage value. That means if you have V plus as your if your feedback is at V plus, so you are trying to fix it at the voltage of V minus. So it is kind of fixating of a voltage to a desired value. That is only achieved by negative feedback. Okay. So you should
Yes,
always be cautious about this point. So there will be some tricky questions where it may seem that your device is in negative feedback, but you should always check that if your device is in negative feedback or not first. Okay. And then you apply this virtual short configuration. So once you are sure that this is in negative feedback and you can apply your virtual short condition, then your Vx will be 0 because your V plus here it is grounded, right?
sir.
So then, yeah,
Sir, procedure to check negative feedback or positive feedback. We have to
yeah,
write
yeah.
a transfer function, or
No, no,
how
no,
can
no,
we?
no, 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 no. You do not need to write a transfer function. I'll just tell you that. So your V in by V out will be minus RF by R in, R1. So in this case, it is nothing but minus 10. Okay. So now procedure to check negative feedback. Okay. Yeah, I think it is on now. So you are able to listen to me, right?
Yes, sir.
Okay, okay. So let's continue. So the procedure to check negative feedback is that suppose you are given any circuit, okay? So let's say we take our circuit and we just have something connected in the feedback path. It can be any not, let us use this symbol. It can be anything. Okay. So what you need to do, first thing is you need to break the loop. Okay, fine.
Yes, sir.
So you need to break the loop and you need to start, let's say you are increasing. Up arrow means you are increasing the potential, down arrow means decreasing the potential. Okay, so you are using up arrow here. So this node voltage is increasing, right? Because it is directly connected. Fine.
Yes, yes, sir. Fine.
Now if this is increasing and let's say, so what will be the value at this point? Will it increase or decrease?
Sir, at output point, which point, sir?
Yes, at output point.
Increase.
So your V minus is increasing, right? So
Yes,
your
sir.
output is what? V out is basically A time
10 into
your
difference.
AD times V plus minus V minus, right?
Yes,
So your
yes, sir.
this is increasing. So your output should be, this is your V minus, right? And this is your V plus. This is your open loop gain. So what will be your V out? V out will increase or decrease?
So difference increases, so it will increase.
Your V minus is increasing.
Yes, sir. V minus increasing, but V plus is at
Fixed
ground is
value.
at fixed value. The fixed
So
minus 5 plus again it increases to minus 7. The difference will be minus 7.
so
So it will increase.
no, no, you're consider the sign also, right?
Okay.
So consider the sign also. It is not necessary that your V plus should be at ground. It may be at any, let's say 10 volt. And your V minus was earlier 2 volt and now 3 volt. So
Then
earlier it,
decreases.
obviously, right, you should consider sign also. So let me
Yes, sir.
mention this, should consider the sense of sign as well. So your V is decreasing, right?
Yes, sir.
Now what you need to check, that at this point, what is the sense of the signal? How do you determine that? Will it increase or decrease? That will depend on the transfer function at this place, right?
Yes, sir.
So let's say if h of s is a, so h of s is, this is input side, this is output side. Okay,
Yes, sir.
so if h of s is a, then this will decrease. So your OPAMP is in negative
Negative
feedback.
feedback. Yes, sir.
Now let's say if your h of s is minus b,
positive feedback.
then your OPAMP, then your this sign will be what? This will also increase. So at the
Yes,
same node, you can see at the same node, by increasing some fluctuation or incremental increasing something, your output is also increasing. If you break the loop, that means that point is getting accumulated. Okay, that is in positive feedback.
yes, sir.
So don't blindly trust that if you're in a op-amp, if your negative or the inverting terminal, if connected to feedback, then it is showing your negative feedback. Okay, that is not true always, because what is connected to your feedback path or the beta is very important. If beta has a negative gain, then obviously that sense of feedback will get doubled. That means negative of negative feedback, or it will give you a positive feedback. Okay.
Yes,
So
sir.
you see on the same case, by connecting the feedback at the minus input or the inverting input of the op-amp, we have got both positive feedback and negative feedback. So now you know without writing the transfer function how to check that.
Yes, sir.
Just use this arrow diagram, take the signs into consideration, you will be easily able to get the sense of feedback. Okay.
Yes, sir.
Okay. And also please remember this point. This is very important. So virtual short only works when your op-amp is ideal and it is connected in your negative feedback configuration. Okay,
Yes, sir.
so let's move on. So now from the above discussion, this should be very clearly answered. The phase shift offered by the positive feedback circuit is either,
Either 0 or 360.
why do you say that? Because then only it will add in phase, right?
Yes, sir.
So that is what you have been asking and also we have been discussing, right?
Yes, sir.
So basically, again the same principle. This is plus and this can be plus or minus. Let's say this is A. So what we do? We break the loop. Okay. Or if let's say you do not have the access of eraser, so what you can do? You just break the loop here. Take this point, or let's just kind of making it an open circuit. Okay.
Yes, sir.
Check the sense that what is happening here and what is happening here. So if these two, you can break the loop at this point also, or let's say at this point also. So by the way, there is also another interesting point I did not mention. Where should you break the loop? That is also important, right? Have you understood what do I mean by breaking the loop?
Sir, here only one path is there, so that path will be break.
Let's say you have multiple paths.
For example,
For example, you have multiple paths or interconnected feedbacks. Okay.
okay,
Then what can see the golden rule or the thumb rule is break the loop at the node which has a high resistance.
okay.
Okay,
Yes, sir.
there is a inherent reasoning for that, because you know what, high resistance, first thing it comes to your mind that it will be at the gate. Okay,
Yes, sir.
so if you apply any input at that gate, so it will automatically translate to the current at the output side, so you don't need to do anything. And
Yes,
now
sir.
suppose you are breaking the loop at the output side, then it will be difficult for you to fathom that what is the input side voltage excursion or diminishing effect. Okay, so
Yes,
that is
sir.
why it is always suggested that break the loop at the input at the node where the input resistance is higher. So let's say in this path you break the loop at this point. So this is your input. If this is increasing, input is increasing. If this is increasing, this will increase, this will increase. Now depending on whether it is plus or minus, this value will increase or decrease. Okay, and so this is determined by if adding in phase or out of phase. If adding out of phase, that means 180-degree phase shift. If adding in phase, that means 0 degree or 360-degree phase shift. So this corresponds to your positive feedback and this corresponds to your negative feedback. And from this, there is another famous rule for oscillation. Have you heard of this thing?
Sir, heard but not remembered. Long time ago.
So Barkhausen's criteria is what? That for sustained oscillation, your modulus of A beta, these two, should be 1 and angle of A beta should be equal to 2 pi n, and n belongs to 0, 1, 2 and so on. So oscillation means by default you have to have positive feedback, right?
Yes,
And
sir.
what is the phase difference? 2 pi is what? 360-degree.
Yes, sir.
N is 0 means 0 degree, 1 means 360-degree, 2 means 720-degree. You see? So from this Barkhausen's principle also you can answer this question if you remember that thing.
Okay.
So let's move on. So can you answer this question? The inverting op-amp configuration suffers from. So low gain, is it a concern?
No, sir.
Because I can anyhow increase the resistance ratio, right?
Yes, sir.
So this is your R2. Let's say this is your R1. This is your V in. This is your V out. So low gain is not a concern because my R2 by R1 I can make increase to the order till the op-amp does not enter into saturation. Okay, I can increase my R2 by R1. High power consumption, is that an issue?
No, sir. We will supply power.
Power supply will determine that. Until the extent my it touches the power supply rails or these two saturation rails, my op-amp output will start to saturate, right?
Yes, sir.
And what about input resistance? High input resistance is anyhow desired,
Yes, sir.
so that is not a suffering to us. What about
Yes.
low input resistance? What do you think is the input resistance?
Uh, sir,
If I
suffer.
connect V-test here, no, what is the value? And this is
Infinite.
I-test.
Uh,
What is
sir,
Rin?
very, very high.
No, no, you answer me the exact value from the figure.
R2,
if you can answer this one, I will assume that you understood the at least the common ideal op-amp circuits. This is very easy. Let me tell you that much.
Sir, R1 in series is R2,
R1 in,
series with R2.
okay. So let's say you have, you are telling this, right? So this is your V out, this is your V in, this is your R1, this is your R2, right?
Yes, sir.
So that is happening when, and this is let's say your V test, fine, and this is
Yes,
your I test. So your V test by I test, what do you think? It is R1 plus R2. There has to be a path till ground, right?
yes, sir.
Don't you see that this node is grounded?
Yes, sir.
This node is grounded.
yes, sir.
Fro-
दोनों पैरेलल में होगा.
Why will it be parallel again?
Sir, one is grounded and no, sir. I do,
No, no,
neither in parallel nor in
don't,
series.
don't think from that point of view. What, what do you have? You have a branch at this location, right?
Yes,
You
sir.
need to find out the current in this branch only. What is the current in this branch? You know two terminals voltages. You know the resistance. What is the current? This is the same branch as this one, right? You know this is VA. Let's say this is VB. You know VA is V test. You know VB is 0. You know the resistance between is R1. What is I1 or I test? V test minus 0 by R1, isn't it?
Yes, sir.
So what is your input resistance? V test by I test. What is V test by I test? Simply R1. Do you get that?
Yes, sir.
So you need to see that what is the current flowing in that branch. Okay. Forget about any other branches associated with it. If that voltage is ground, that means this point is fixated. It is equivalent to connecting a voltage source of 0 volt to this node. Okay.
Yes, sir.
So that means what is the current flowing will be V test by R1 only. And that R1 will appear as at the input resistance. Okay.
Yes, sir.
So instead of infinite resistance, R1 is your input resistance. So R1 is generally lower, right?
Yes, sir.
Why? Because your gain is R2 by R1. If you want to increase your gain, you want to keep your R1 lower so that you can increase your overall gain. So for that matter, your input resistance basically suffers. Okay.
Yes, sir.
This you understood, right?
Yes, sir.
Okay.
सर इसका सॉल्यूशन क्या व्हाट इज द सॉल्यूशन ऑफ दिस
Which one?
वी हैव टू आर वन को हमें कम करना है और इनपुट रेजिस्टेंस ज़्यादा होना चाहिए.
Okay, okay. Solution.
यस सर.
Have you heard of this guy? It is also an, Have you heard of this instrumentation amplifier?
No, sir.
Just Google it or search it anywhere. It is similar circuit connected in a coupled manner. Okay, the way we have done it in for the it as in your single-handed op-amp to double-sided differential pair. The same philosophy is applied here also. Okay, two inverting amplifiers are connected back to back. A resistance is in a common resistance is there in between, and that those output are fed to another op-amp. Okay,
Okay.
so you just search it instrumentation amplifier and you will get to know that. That is actually used in industry also in many control systems. This you should be aware of if you are appearing for gate. Okay, questions comes from this thing.
Yes. सर yet I not started OPAMP. अभी
Okay,
मॉसफेट में ही फंसे हुए हैं. बस नेक्स्ट वीक से ओपन करना शुरू कर देंगे.
okay. There is no problem, but try to cover up all the op-amp circuits. Okay, all the possible op-amp circuits, including
Yes,
Smith trigger and all. Okay, where the
yes, sir.
positive feedbacks
In
are
this week
there.
and next week, I will finish OPAMP.
Okay, so yeah, now it is that which of the following plots correctly describes the V0 versus VI relationship for the circuit shown in the shown in the figure. So this is the following questions what I am going to discuss now are very important for GATE exam. Okay,
Yes, sir.
so look it from those point of view. So I just want to know your approach. If I ask you that this question came to you suddenly, how do you want to approach this question? Means what do you see in the question, and you so that I just don't want to give you the solution. I just want to know how you should approach the problem. You start telling me that what are you seeing in the circuit? What is this basically? What is this guy?
ये पिछला वाला सर्किट.
That is your inverting amplifier, right?
Yes, sir. Inverting amplifier.
What is this one?
Diode.
Which diode is this?
Zener diode.
So whenever there is a question of Zener diode, what do you keep in mind?
Uh,
What is the transfer characteristics of Zener diode? Let's say this is VD and this is ID. So this is ID, this is VD. How should it look like?
it support reverse saturation.
So in forward direction, it is just a forward bias diode.
Yes, sir.
In reverse direction, it will just flow current and it will suddenly drop.
Yes, sir.
This value we call it VZ or the Zener
Yes, sir.
voltage, right?
Yes, sir. VG.
And this is what is this value? If it is silicon diode,
0.7.
0.7 volt. Fine.
Yes, sir. Yes, sir. 0.7 volt.
Now, what can I approximate this value? What can I approximate these two curves as?
Constant.
No, in from circuit terms, what are
Uh,
these? You
voltage
have
is constant short circuit.
no. Your voltage is constant. Current can be any value.
Open circuit.
No, from fundamental elements of the
Voltage
so
is. constant current.
So if I give you this, how will the IV characteristics look like?
Okay.
How will it look like?
Uh, Constant current will be same regardless of the voltage.
Now if I give you this, how will the IV characteristics look like?
Uh, Sir, why opposite? Voltage will be same current
Right?
regardless of current. Yes.
So can you see this is a voltage source?
Yes, sir. That is a voltage source.
So this is a voltage source of 0.7 volt. This is, let's say this is 5 volt. See, this is a voltage source of minus 5 volt. But there is a region where it is kind of isn't flowing, right?
Yes,
Current
sir.
is zero means in this region, what is this? Current zero means,
Open circuit.
okay?
Yes, sir.
So you see what is happening basically. It is kind of a voltage source, right? Let's say
Yes, sir.
these were your two values. This is one value and this was one value. This was the voltage source you had. Now what you have done? You have taken this guy and shifted it like this. Okay?
Yes, sir.
So Zener diode is generally used as voltage referencing. You know that, right?
Yes, sir.
To create a
Voltage
reference
reference.
voltage. So that the
Sir,
reason behind this is because it creates a constant voltage.
yes, sir.
Okay. So now tell me, you have basically this is grounded. This guy doesn't matter. By the way, why did I say that RL doesn't matter? OPAMP is what? A VCVS or VCCS or CCVS or CCCS? OPAMP is which kind of control source?
I don't know.
Come on here, you can try it. Which kind of control source is that? What is the input of an OPAMP?
A voltage.
What is the output of an OPAMP?
Sir,
So
V out ही निकल रहा है voltage only.
V out
Voltage
is equal
control
to
controls.
V out is equal to AD times delta V, right?
Okay.
So
Yes,
this
sir.
is your voltage. This is your voltage. So what is this?
Voltage control voltage.
Obviously, right?
Yes, sir.
So you have your V0 fixed at this point. Once you know your V0, so it doesn't matter if you know your RL or not, right? So RL is just to keep you thinking that if you should use that RL, what is the purpose of RL if you don't understand the circuit or these concepts clearly. Okay, you will lose your time in your exam. So now what we will do? So we have how many cases? This is, let's say, case 1, this is case 2, this is case 3, right? We have three kind of cases. In one case, it will be a zero point 0.7 voltage source. In another case, it will be
Minus 5 volt.
minus 5 volt. In another case, it will be just an
Open
open
circuit.
circuit.
Yes,
Fine.
sir.
Now
Yes,
just
sir.
we need to find out what are these regions. Okay.
Yes, sir.
Now let us just start with keeping the symbol as is. Now let us start. So by the way, if Vi is 0, what is V out? Vi 0 means this is also 0,
Yes,
right?
sir. That is, yes, sir.
So
0.
V out will also be 0.
Yes, sir. 0.
So first thing is that all the means your V out versus Vi should pass through the origin. Do you get this point?
Yes, sir.
Okay. So now what we'll do? We'll keep increasing Vi. Let's say let us start keep increasing Vi. So if I increase my Vi, this will increase. Okay.
Yes, sir. Yes, sir.
So where I am actually I am at this range, this range. So at this range, this will be treated as,
Open circuit.
then my entire circuit diagram will be
Inverter.
not
Inverting
inverter,
amplifier.
inverting amplifier,
Yes, sir. Inverting amplifier.
and V out by V in will be, this is R, this is 2R. So V out by V in will be
2R by R. 2
minus 2,
minus 2.
right?
Yes, sir.
So if I start to draw my V in versus V out, so it will be something like this.
Yes, sir.
After some time, when I increase it much more, this diode will turn on. So now what do I have?
A constant voltage.
I have a constant voltage source and I have a 2R resistance, right?
Yes, sir.
So can you tell me what is the current flowing through this branch and what will be the current flowing through this branch? How much current do you think there will be flowing in 2R resistance? What is the series resistance of an ideal voltage source?
Infinite.
Are you sure?
No, sir.
Series resistance of an ideal voltage source is zero, right?
Yes, sir. 0. इनफाइनाइट होगा तो सारा तो वहीं ड्रॉप हो जाएगा.
Exactly.
सॉरी.
Infinite will be open circuit only, right?
यस सर.
So in this path you are seeing zero resistance and in this path you are seeing 2R resistance. So all the currents will be directed through this path.
यस सर.
It will be as if this is not present or this is open circuited.
यस सर.
So if this is your V out, so what will be your V out then? This is your grounded, right? From your virtual short configuration. So what is your V out? So let me simplify the circuit for you. So this connection is now, there is a resistance. This is connected. This is 0.7 volt. And I am telling you that this is grounded. So what is V out? What is V out?
Sir, 0.7 volt.
Are you sure?
Sir,
Look at
it's
the
low
sign.
like that.
Look at the
Minus
sign.
0, minus 0.7 volt.
So it is minus 0.7 volt, right?
Yes, sir.
So you see that much, right? Now can you
Yes,
see
sir.
when you just start to decrease this V in below zero? See, when it is in this region, it will keep increasing like an inverting amplifier because it will keep doing this thing.
Yes, sir.
And after that, when there will be a 0.5, when there will be a minus 5 volt value of voltage source, then again it will be, V out will be saturated to plus 5 volt.
Yes, sir.
So which kind of characteristics are there? This is crossing through 0, this is crossing through 0, this is crossing through 0. So this will be your correct option.
Yes, sir.
So now tell me, have you understood this part or not?
Yes, sir. Understood.
So negative part, please explain me that below 0 what will happen? When V in is getting lesser than 0, then your this region it will encounter first for the diode. So
Yes,
the
sir.
diode
Open,
will remain open circuit
open
and your
circuit.
entire circuit will becoming an inverting amplifier
Inverting amplifier.
having a slope of minus 2.
Yes, sir.
So basically if I am increasing V volt here, it will increase 2V volt minus direction
Yes, sir.
because I am increasing in the negative x direction, right?
Yes,
So
sir.
y will be direct increasing in the positive x direction twice because the gain is minus 2. It will
Yes,
reach
sir.
till this point until when then again another voltage source will appear in parallel. But now the sign is opposite.
Yes, sir.
So you see this is such a simple problem. Once you understand the concepts, this problem is very simple, okay?
Yes, sir.
So these kinds of problems are very important for your GATE exams, okay? So please pay
Yes, sir.
attention to the concepts. Then moving on to this, what is the transfer function of this for the circuit shown below? So how to do this very quickly? So if you have understood that this entire stuff, this entire stuff is your inverting amplifier, right?
Yes, sir.
But this reference voltage is determined by something else, okay? Not
Yes, sir.
grounded this time. So what
Yes,
will
sir.
happen? This current will be equal to this current because no current should flow in this, assuming ideal op-amp, right?
Yes, sir. Yes, sir.
So your, let's say, so this will also be Vx. So Vi minus Vx by R2 should be equal to Vx minus V naught by R2. Is that okay?
Yes, sir.
So Vi will be equal to Vi minus 2Vx equal to V naught. Fine. And what
Yes,
about
sir.
Vx? Vx is equal to Vi times R1 over R1 plus 1 over SC because this is your voltage divider.
Yes, sir.
So that is your SCR1 over 1 plus SCR1 times V in. Now put it here minus 2 times SCR1 over 1 plus SCR1 times VI equal to V naught. So that will be your VI times 1 minus SCR1 by 1 plus SCR1 is equal to V naught. So your V naught by VI is equal to 1 minus J omega CR1 by 1 plus J omega CR1. So that is 1 minus J omega by omega 0, let's say, divide by 1. By the way, there is a minus sign here, plus J omega by omega naught, where your omega naught is equal to 1 over CR1. So this is in the form of this. Is it understood?
Yes, sir.
So where is the means this is doing the thing very quickly, okay?
Yes, sir.
By the way, you have noticed, right, that I had earlier mentioned, I earlier missed this minus sign, but immediately strike to me that there is a minus sign missing. How do I know that?
Inverting amplifier to
Exactly,
Z,
right? So
Z
because
by
my
Z minus
subconscious
Z by
was
Z.
telling me, exactly, my subconscious was telling me that the gain has to be negative quantity.
Yes, sir.
So this is a sanity check you should keep in your mind while you solving the problems, okay?
Yes, sir.
So what is the value of K now then? K is your minus 1, okay?
Yes, sir.
If you compare with this one.
Yes, sir.
So moving on to this, okay,
सर ये के जो गेन होता है इसका
yep.
क्या रिलेवेंस होता है?
The relevance of K,
यस सर.
relevance of K will determine, okay. So did I mention this type of form in the last class that gain times 1 plus S by Z1 by 1 plus S by P1 transfer function forms?
यस सर.
So if you put S equal to 0 or omega equal to 0, what is A?
सर वो तो ठीक है के मतलब जो गेन.
That is a DC gain, right?
यस सर डीसी गेन.
At
बट सर
DC, yeah,
डीसी गेन means when no AC supply, just like in MOSFET, the biasing part is DC gain. We can say that.
yes.
Okay.
Basically, when you draw your Bode plot, right?
Yes,
So
sir.
this is the gain.
सर ठीक है. अगला क्वेश्चन कीजिए फिर हम लोग डाइवर्ट हो जाएंगे.
Okay.
Okay.
So going to the next one, for the OPAMP filter shown in the figure below, filter type. So can you tell me the filter type immediately by looking at the circuit? How to check the filter type? Last class I have mentioned. So is it not visible? Is the screen visible? The next question.
Yes, sir. Visible. No, sir. Question number
Screen
8 is visible.
screen is frozen, right?
Yes, sir.
I don't know what happened. Let me just reshare the screen. I don't know what is happening today. So this was the last thing what we have discussed. Now this is. So what is the filter type? Can you tell me immediately by looking at the filter? How do we check that?
Sir, one capacitor is the.
No, no, we need to just check the transfer function, right?
Yes,
And
sir.
assume that what is our at zero frequency how it behaves, at high frequency how it behaves. So at zero frequency, what will happen? When A is equal to zero, your C will be open or short.
Open.
So your output will be
Inverting amplifier.
your R2 by R1 times V in, right?
Yes, sir.
So it will have a certain value. And what about your at A is equal to infinity? C will be
Seal close.
C will be short. So what is your V0?
V0 is
Note the virtual short,
sir, the ground zero.
0, right?
Yes, sir.
So it will be something like this. So what is this filter?
And this is band pass filter.
Come on, how can this be band pass filter?
Uh, Low pass filter, sir.
This is low pass filter, right?
Yes, sir. At zero low pass filter.
So you can immediately tell from the circuit that this is low pass filter. Fine.
Yes. Yes, sir.
Now you need to find out the 3 dB frequency. That means you need to find out the pole location. So how do you do that? You just need to write the transfer function.
Yes, sir.
So can you immediately tell me what is the transfer function? What is the gain? Minus, this is now my R2, right?
Yes, sir. Minus.
Minus R2 parallel 1 over SC divide by R1. Is that okay? Can I write it
Yes.
directly?
Yes, sir.
So what is that? R2 is 1 over R2 plus SC divide by R1. So that will be R2 divided by 1 plus SCR2 divided by R1. So your P1 is equal to 1 over CR2. That means your F1 is equal to, or F3 dB, let's say, is equal to 1 over 2 pi times C is what? C is your 50 10 raised to minus 9. R2 is 8.2 10 raised to 3. So if you solve it, you will get it is at 388 hertz. Okay.
Yes, sir.
So I am just showing this to you to show that how to solve the problems very easily by just noting that you understood your inverting amplifier very clearly. Is that okay?
Yes, sir.
Just by looking at the circuit, you can conclude that it is low pass filter. So you can
Yes.
immediately know that this you should not be worried about. Now you need to worry about the cutoff frequency. To know the cutoff frequency, what you will do? You know the inverting amplifier gain. You just connect entire stuff, right? Whatever I connect here, it does not matter because these two terminal you know, whatever current will flow here, it will flow through this point only. This will always be virtual short, right?
Yes, sir.
So consider it as a Z, an impedance, and then do the formulation. It will be Z minus Z by R1, and Z you can find out by your combination of parallel combination of R2 and C. Okay. So try to do these problems very quickly. It should not take you more than 20 seconds to solve these problems. Okay.
यस सर. सर लो पास फिल्टर से सर हमें क्या पता चला?
Low, there are options, right? Whether it is high pass or low pass.
ओह यस सर. यस सर.
So you have to discard the unnecessary options, right? Which are not correct.
यस सर.
So your focus can only be at finding at the frequencies.
यस सर.
So what is the form of the transfer function? Okay. So again, it is a good practice for you. Can you tell me the how this will look like? If it is a low pass, band pass, high pass, band stop, just try it out. Put your S equal to 0. Your capacitor will be,
ओपन सर्किट.
capacitor is open. So your V0 will be,
आर आर टू
V,
बाई आर वन
capacitor
माइनस
is
आर टू.
open.
ओके तो नो इनपुट जीरो.
So V0 will be 0. And what if your high frequency capacitance will be short? It will be R2 by R1, right?
यस सर.
So it is what kind of filter?
हाई
What kind
पास
of?
फिल्टर.
It is high pass filter, right?
यस सर.
So immediately by looking at the circuit, you can conclude that it is a high pass filter.
यस सर.
So now the nature of high pass filter is that at zero frequency, the output is zero.
यस सर.
Fine.
यस सर. हाँ. यस सर.
At
जीरो फ्रीक्वेंसी आउटपुट इज जीरो.
at omega equal to 0, h of s is 0,
यस सर.
or not h of s, your out, yeah, h of s is 0, and thus your output is 0.
यस सर.
So what do you think? There should be a pole at, sorry, there should be a 0 at s equal to 0. Can I
यस सर.
conclude this? So immediately from the option you can tick this one, right?
यस सर.
So your 0 location is here, your pole location is here. You can immediately check.
यस सर.
In other way, you can simply just do the solution. Your V0 by V in will be R2 by series combination of 1 over SC, that is SCR2 divided by 1 plus SCR1, that is J omega CR2 divided by 1 plus SCR1. So your K times J omega divided by 1 plus J omega by omega 0. So what is your K? K is equal to minus CR2. What is your omega 0? 1 over CR1, right?
यस सर.
So you can, by inspection, you can solve this problem if you know this, how to draw these functions or
यस.
the Bode plots. Okay. So let's
यस
move
सर.
on to the next problem. What is the form of the transfer function of this? Okay. So how do you do that? Here, do you know the V minus or V plus input? You do not know, right?
यस सर.
So you assume it to be Vx. So your Vx is equal to V in times R by R plus 1 over SC. This I am writing from this voltage division.
यस सर.
So this will be Vi times SCR over 1 plus SCR. And what about the other loop? This one, 0 minus Vx by R1 is equal to Vx minus V out by R2.
Yes, sir.
So your V out by R2 is equal to Vx by 1 over R1 plus 1 over R2. Now your V out by R2 is equal to Vx is what? Your V in times SCR divided by 1 plus SCR times 1 over R1 plus 1 over R2. So your V out by Vi will be SCR divided by 1 plus SCR times, if you multiply R2, it will be 1 plus R2 by R1 times this. So what is the form? J omega is there. So this is the form, right?
Yes, sir.
So this is your K and your omega is, omega 0 is, no, not this is not your K. Your K will be CR times 1 plus R2 by R1. Omega naught is 1 over CR. Okay?
Yes, sir.
You just need to put this as J omega. By the way, have you noticed that this is an inverting amplifier? A non-inverting amplifier? It is similar to this configuration, right? Is it okay?
Yes, sir.
So what is the V naught by V in? 1 plus R2 by R1. This you know, right? For a
Yes, sir.
non-inverting amplifier.
Yes, sir.
So have you noticed that when you're at high frequencies, your C will be short, then it is same.
Yes, sir.
That is why your this flat portion of the gain is coming at as this. So if you solve this, it will be something like this, where this gain will be 1 plus R2 by R1. Okay.
Yes, sir.
So let's move on to the next problem. Okay. So an OPAMP circuit is shown below. Voltage input voltage waveform is this. We need to find out the output voltage waveform. Okay. So what we'll do? We'll break it into positive half cycles and negative half cycles. Okay.
Yes, sir.
So when it is 0, this is connected anyhow in negative feedback. By default we can see. So this will be 0. So everything will be 0. So V out and V in, this is connected to 0. So these points will be 0, right?
Yes, sir. Passing through origin.
Passing through origin every time. Or in this
Yes,
case, 0 line, because we are talking about time axis as x axis. So now what do I need to do? I need to check the input when this is my upper half, right?
yes, sir.
So there will be a upper half means what? This is increasing, so this will also increase. Diode will get connected, so this will be kind of a short one. So
Yes,
once
sir.
it is short, What is this configuration? This is V in and this is just short. What is the configuration of this? Your V out is equal to what?
Infinite
No,
R2
there is
R in.
nothing. Don't think about R2 and R in. Think about virtual short. It is in negative feedback ideal op-amp.
Okay.
So your negative terminal sees which voltage
V in.
and your V out and V in is connected. That means what? Your V out is,
V in.
so it is unity gain, right? It is kind of
Yes,
a
sir.
buffer.
Yes, sir. This is buffer.
So at positive half, output will just mimic this one.
Yes, sir.
And what about negative half? When this is negative or this will go down, so diode will be open, right?
Yes, sir.
If diode is open, this is connected to this and this is connected to ground.
Yes, sir.
No current is flowing, right? That means it
Yes,
is
yes.
connected to ground in a sense. So that
Yes.
means the output will keep at 0. Again, it will go up, it will follow this and output will go at 0. Okay.
Yes, sir.
So your, and if there is inverting, no, it is not inverting. So this will be your right answer. Okay. So if you start doing the op-amp circuits next week, I suggest you to go through any standard book and try to solve the exercise problems, okay, of that ideal op-amp.
Yes, sir.
But remember, solving in ideal op-amp circuits, 2 points: that virtual short only you can use when the device is ideal and you have negative feedback in place. And if you want me to discuss about the positive feedback circuits like Smith trigger and all, I can discuss it in the summary session. So I think that is, yeah. So there is an announcement that no session will be there on next Sunday. Okay. That session is postponed to 18th. You will get the notification accordingly from IIT Madras team that from 6 to 8 p.m. Friday we'll have the 12 week 12 session. So that I'll do as per the professor as teaching in the class, what are the topics he has covering. In the summary session, I can that will also be a 2 hour session. So I can show you uh, about the topics of your interest if you need some clarification or not. So what I'll do, I'll post a Google form link in today's YouTube video comment section. Okay, you just fill that form and mention me that what are the topics you want me to discuss, or you need more depth, or you want some rediscussion. So I'll discuss those things. Okay.
Sir, can
Yeah.
we fill the form before like 18 or 19? Because I have not gone through the OPAMP. If I go through the OPAMP, then
Yeah, no, no.
I will
I'll
realize.
I'll I'll keep it open till 19th. Okay. How does that
Okay.
sound?
Okay.
Okay, just let me know if you want anything to be discussed on BJT, MOSFET, diodes from the circuits point of view, noise margins and all. Okay.
Yes, sir.
Okay. So I think that's all I have today. So let's meet you on 18th.
Yes, sir.
Okay.
Thank you, sir.
Thank you.